Today I'm going to talk to you about WatchTower, which is a new system that enables fast mobile page loads in a secure way. And this is joint work with Anirudh from NYU, James from Harvard, and Hari from MIT. So let's start by quickly reviewing the page load process. To load a page, a user first types a URL into her browser, let's say amazon.com, and the browser will then issue a request for the page's top-level HTML object. And upon downloading it, the browser will parse the response, and it'll then fetch and evaluate any referenced external objects like JavaScript and CSS files. And the evaluation of any of these objects can trigger subsequent objects to load as well. And as this recursive process continues, the browser will progressively render the page for the user until it's fully loaded. And so collectively, this process can be modeled as the browser loading a dependency graph, which is a directed acyclic graph that specifies both the objects to load and the order to load them in. And so in this graph, each node represents an object in the page, and an edge means that a browser must fetch and evaluate a parent before it learns that it has to do the same for a child. And this dependency graph abstraction can also help us think about page load performance. So to fully load a page, a browser must fully traverse a dependency graph, fetching and evaluating all of the referenced objects. And the time that it takes for the browser to do this is what's called the page load time, which is the predominant web performance metric used today. But as you can see from this graph and from the load process in the previous slide, network latencies can play a pretty big role in the resolution of a dependency graph. And the reason is that at each level in this graph, a browser must fetch and evaluate an object before it can discover subsequent objects to load on say, the next level. So for example, in this graph, the browser would first incur a round trip to fetch the page's top-level HTML, and only after fetching it and parsing it will it then discover that it has to fetch the objects on the next level of this graph, like this JavaScript file. And this process will repeat as we move down the graph. And so based on this, really we can put a lower bound on the page load time by looking at the longest route to leaf path in the dependency graph, which I'll call the critical path. And on mobile networks where more and more page loads are taking place and access link latencies can commonly reach 80 or 100 milliseconds, network latencies can significantly inflate this critical path time and thus page load time. And this is a pretty significant practical problem given the numerous reports that have noted the strict performance expectations that users have for their page loads. And so as a result, there's been many efforts to reduce the negative impact that network latencies have on page load times. So one approach is to use HTTP2's server push feature, which allows servers to proactively push resources to clients in anticipation of future requests. So for example, when a client requests the page's top-level HTML, the web server, upon serving the HTML, could guess that the client will soon make a request for referenced JavaScript or CSS files. And so the web server could then push those to the client along with the HTML, so the browser could serve them from cache when they're needed. But even though this could be beneficial, unfortunately, server push has witnessed pretty minimal adoption. And there's two reasons for this. So first, configuring push policies is difficult. So in cases, for example, where there's limited network bandwidth, pushing resources from one domain can actually slow down the fetches of resources from other domains that may be needed earlier in the page load process. And second, using server push inherently requires web servers to understand the resources that comprise a page so that they can determine what to push. But for a given page, this set can change frequently, and some resources can only be discovered by fully loading a page. And so one way to overcome these limitations is to use what's called remote dependency resolution, or RDR. And so with RDR, a client sends its request for the page's top-level HTML to a well-connected proxy server. The proxy will then fully load the page locally using a browser. And as that browser loads objects from origin servers, it'll stream them back to the client's browser, which can then cache them locally. So in this way, RDR proxies are able to resolve an entire dependency graph for a page using low latency proxy links to origin servers, and clients can then limit the number of costly round trips that they have to incur over their slow mobile network links. But even though RDR is able to overcome a bunch of server pushes challenges and the potential benefits are high, it too has witnessed pretty minimal adoption. And there's two big reasons for this. So first, an increasing fraction of web traffic is now served using HTTPS. And this forces RDR proxies to essentially choose between performance and security. So on the one hand, RDR proxies can perform full RDR, where they load all of a page's objects on behalf of a client, regardless of whether or not they're served with HTTPS. And so this could achieve good performance, but it violates a core security guarantee of HTTPS, which is end-to-end encryption between clients and origin servers. On the other hand, proxies can perform what's called HTTP-only RDR, where they only load the increasingly small fraction of web content that's HTTP. But this, of course, limits potential performance gains. And the second practical challenge with RDR is that it doesn't always improve performance. So existing RDR systems like the Opera Mini browser are always on, in that they will always proxy all of a client's page loads. But in certain settings, depending on the network latencies between clients, proxies, and origin servers, as well as the dependency graph for a given page, RDR can actually slow down the page load. So as a quick outline for the rest of this talk, I'll first describe several measurement studies that we conducted to better understand these challenges. And based on our findings, I'll present two solutions. So the first is HTTPS sharding, which is a new RDR scheme that better balances security and performance. And the second is selective proxying, where browsers use knowledge of current network latencies and page dependency graphs to only use a proxy if it's predicted to help. And finally, I'll discuss WatchTower, which is a system that we built that incorporates these two techniques to outperform existing RDR and server push systems by around 30%. And so before I get into the measurement studies, a few quick notes about our experimental setup. So to evaluate RDR, we used an open source RDR system called Cumulus, as well as the Google Chrome browser. And with this setup, we loaded the Alexa Top 500 pages in the US over a bunch of live networks in Massachusetts, including cellular, residential Wi-Fi, and in-flight Wi-Fi. So let's start with the first challenge, which was HTTPS. So here are some results comparing default page loads to both full and HTTP-only RDR. And so in this experiment, to focus specifically on the impact of HTTPS and not things like proxy location, all of these results for each page, they use the best of multiple geo-distributed RDR proxies. And there's a few things to take away from these graphs. So first, as you can see, both forms of RDR outperform the default page loads. And the reason is that they're able to reduce the number of costly round trips incurred over those slow mobile network links. Second, full RDR consistently outperforms HTTP-only RDR, providing roughly 1.5 to 2 times the benefits. And the reason is that full RDR is able to save a larger number of round trips by proxying all page content rather than just HTTP content. And both of these trends are more pronounced as network latencies grow, so as we move left to right in these graphs, because the benefit of saving each additional round trip is higher when the network latency is higher. And so clearly these results pose a tricky trade-off. As I mentioned, RDR can either achieve high performance and sacrifice security, or they can preserve security with minimal performance gains. And so to ease this tension and to get both high performance and security preservation, we developed a new RDR scheme called HTTPS sharding. And so with HTTPS sharding, intuitively, each HTTPS origin runs its own RDR proxy, which can serve HTTPS content that it owns, as well as HTTP content from any origin. And even though this seems fairly simple, it actually leverages an interesting property in web page dependency graphs, which is that the HTTPS objects for a given origin are typically clustered into subgraphs. And so this limits the number of times that a client has to actually contact each origin's proxy. So for example, consider this simple dependency graph. With full RDR, a proxy would be able to load all of this page's objects, while with HTTP only, the proxy would essentially have to ignore objects 3 through 8. With HTTPS sharding, the proxy for origin 1 could load objects 3, 5, 6, and 8, and the proxy for origin 2 could load objects 4 and 7. And so with HTTPS sharding, a client does have to incur a few more round trips than it would with full RDR, so it can contact each origin's proxy. But then each proxy can resolve an entire subgraph, thereby loading more objects than it could if it was using HTTP only. And so we evaluated HTTPS sharding using the same setup as before, and we found that it's able to significantly outperform HTTP-only RDR while providing the same security guarantees. So in particular, we found that HTTP-only proxies are able to achieve only 50 to 60% of the benefits of full RDR, while HTTPS sharding is able to achieve over 90% of the benefits of full RDR without sacrificing HTTPS security. So now let's switch gears and evaluate RDR proxies in different settings. So here I'll focus on 3 different parameters: network latency, page structure, and proxy location. So to start, we performed a controlled experiment using 2 sites, the Google and TMZ home pages. And so we loaded both pages in a record and replay emulation setup called Mahi Mahi. And we considered network latencies ranging from 0 to 300 milliseconds between the client and origin servers. And in these experiments, the proxy was optimally placed 0 milliseconds away from the origins, so it was effectively co-located. And here in this graph, we report speedups as the ratio of default page load times to RDR page load times. And so a speedup greater than 1 means that RDR was able to accelerate the page load. And so there's 3 things to take away here. So first, these results reaffirm the point that higher network latencies in fact do lead to increased RDR benefits. Second, and more importantly, as you can see, the TMZ page experiences higher overall speedups, and it in fact begins to achieve speedups greater than 1 at lower RTT values. And the reason, looking at the dependency graph, is simply that the TMZ graph has a longer critical path length. And as critical path length increases, so do the benefits of RDR proxying, since serial chains with even small RTT values can end up summing to these large blocking latencies that RDR can then save. And finally, these results show that there are cases in this experiment where RDR does slow down page loads despite the optimal proxy location in this experiment. And so here, the reason for this is that RDR does impose a computation penalty since the proxy has to also load a page. And so in this experiment, the benefits essentially hinge on the network latency savings having to outweigh that compute penalty. And the potential for RDR to actually slow down page loads only grows when we consider more realistic proxy locations. So for example, here are some results for full RDR when all page loads used 5 different proxies located in different regions. And so as you can see from this graph, the proxy location can have a pretty significant impact on overall RDR performance. In addition, this graph highlights that RDR proxies should be placed as close to origin servers as possible to ensure that resolving dependency graphs is faster using proxy origin links rather than client origin links. And so this is evidenced in the graph by the fact that the California and Massachusetts proxies were able to achieve the highest overall speedups, since 84% of the objects for the pages in our corpus were served from origins in those regions. And so this last set of results motivate that RDR provides benefits in some settings, but not others. And so this challenges the conventional always-on approach, and instead motivates that RDR should be done selectively, where proxies are only used if they're expected to reduce page load times. But doing this requires us to have some way to impact to estimate the impact that proxying will have on performance. And so in order to predict page load times, we again turn to dependency graphs and their critical paths. So recall that the critical path can put a lowered bound on the page load time. But since network conditions can vary both across origins and across time, the longest path in the graph may not actually be the slowest one to resolve at load time. And so instead, our selective proxying technique aims to compute what's called the dynamic critical path of the load, which is the path in the dependency graph that lower bounds page load time based on current network conditions. And so at a high level, the way that this works is that we estimate the resolution time for each path in the graph in isolation, and then we estimate the page load time to simply be the time of the path that's predicted to be the slowest. And so let's see how this would work for a simple example dependency graph. So estimating the page load time for a default page load is fairly straightforward. At a high level, the client has to resolve each edge in the graph on its own, directly with origins. And so each path's load time is simply its length times the RTTs to the appropriate origin servers. To estimate RDR page load times, we do have to use a different technique per RDR scheme. And so I'll quickly run through an example here for HTTP only, but the paper discusses how we handle the other schemes as well. So with HTTP only, anytime that in a path that you have an HTTP to HTTPS transition, the proxy essentially has to halt resolution, and the client has to then go and directly resolve HTTPS edges with the origin servers. And the client can only actually go back to the proxy if there's a subsequent HTTPS to HTTP transition. So for example, in this graph, if we consider the rightmost path, the client would first download HTTP object 1 from the proxy, which would then get stuck as it encountered HTTPS object 4. The client would then have to resolve objects 4 and 7 directly from the origins before finally going back to the proxy to download object 8 which is HTTP. So we've now covered these two core techniques to overcome the practical limitations of RDR proxying, which are HTTPS sharding and selective proxying. And so in the rest of this talk, I'll briefly describe a system which implements these two techniques called WatchTower. So the design of WatchTower has two main parts. So there's a browser plugin that supports different RDR schemes, including HTTPS sharding. And then there's a set of RDR proxies which are scattered across the internet. In order to perform selective proxying, WatchTower does need information about current network conditions and page dependency graphs. And so in WatchTower, the proxies periodically measure their latencies to popular origin servers, and they also download the corresponding dependency graphs for their pages. The client plugin then periodically downloads this information from the proxies, and it also measures its latencies to both the proxies and popular origins. And then using this information, page loads are fairly simple. So upon loading a page, the plugin will predict the estimated page load time with the RDR scheme of choice as well as without a proxy, and it'll use whatever is predicted to be faster. So to evaluate WatchTower, we first compared it to an always-on proxying system that always used the proxy that was located closest to the client, which is what existing proxying systems do. And so with WatchTower, WatchTower had access to 7 different proxies scattered around the world on EC2, and the plugins with WatchTower in this experiment were fed the dependency graph and latency information just before the experiment. So as you can see, WatchTower achieved pretty significant speedups compared to the always-on proxying. But interestingly, WatchTower's selective proxying was also quite effective, despite it being fairly coarse-grained and not considering things like TCP window semantics or compute overheads. And so for example, on the Wi-Fi network, WatchTower was able to reduce the probability that a proxy was used when it shouldn't have been from 30% to under 1%. And finally, we also compared WatchTower to different server push systems. So in particular, we considered a push policy where all static resources were pushed, as well as Vroom, which is a state-of-the-art web system that pushes static resources and also uses link preload headers so servers can give browsers hints about objects that they'll soon need to load from other domains. And so as you can see from this table, WatchTower is also able to significantly outperform these systems as well. And there's 2 reasons for this. So first, both push systems can only push static resources, whereas WatchTower is able to accelerate the fetches for both static and dynamically constructed URLs. And second, WatchTower streams objects to clients in the order that they would naturally request them in based on current network latencies. And so it's able to avoid some of the potential bandwidth contention that server push systems can experience. So it looks like I'm running out of time, and so with that I will conclude, and I'm happy to take any questions.